The Story of Everything. Part 1. The Birth of the Universe. The story of the universe begins in a moment so small and so brief that human language can barely describe it. This moment is known as the Big Bang. It was not an explosion in empty space. It was the sudden expansion of space itself. Before this moment there was no time, no matter, no energy, and no space. The universe began as a single point of unimaginable density and heat. In less than a heartbeat, it expanded faster than the speed of light. This event set the foundation for everything that would ever exist. In the first instant, the universe was a storm of pure energy. Temperatures were so extreme that matter could not survive. Particles appeared and vanished in fractions of a second. The laws of physics were still forming. Gravity, electromagnetism, and the nuclear forces separated from a single unified force. These forces would shape the future of galaxies, stars, planets, and life. The universe was learning how to behave. As the universe expanded, it cooled. After a few seconds, the first particles of matter formed. Protons, neutrons, and electrons emerged from the energy of the early cosmos. These particles were the building blocks of everything that would come later. But the universe was still too hot and chaotic for atoms to exist. It was a glowing fog of charged particles and radiation. Light could not travel freely. The universe was bright, but no light could escape. After 3 minutes, the first atomic nuclei formed. Hydrogen and helium appeared. These were the simplest elements. They were the seeds of all future matter. But the universe remained too hot for electrons to join these nuclei. Atoms could not yet form. The universe continued to expand. It continued to cool. Hundreds of thousands of years passed. Then came a moment called recombination. The temperature finally dropped low enough for electrons to attach to nuclei. The first atoms formed. The fog lifted. Light was free to travel. This ancient light still exists today. It is called the cosmic microwave background. It is the oldest light in the universe. It carries a snapshot of the cosmos when it was only 380,000 years old. It shows tiny variations in temperature. These variations were the seeds of galaxies. After recombination, the universe entered a long period known as the cosmic dark ages. There were no stars, no galaxies, only vast clouds of hydrogen and helium drifting through space. Gravity slowly pulled these clouds together. Tiny differences in density grew over millions of years. The universe was preparing for the first light. After hundreds of millions of years, the first stars ignited. They were enormous, much larger than the stars we see today. They burned hot and bright. Their light ended the cosmic dark ages. These first stars began to shape the universe. They created heavier elements in their cores. They exploded as supernovae. They spread these elements into space. This was the beginning of cosmic evolution. The birth of the universe is not only a scientific event, it is the beginning of every story. Every galaxy, every star, every planet, every living being, everything that exists today can trace its origin back to that first moment. The universe began as a single point. Now it stretches across unimaginable distances. It is still expanding. It is still evolving. It is still writing its story. Part 1 reminds us that the universe is not static. It is dynamic. It is changing. It has a history. It has a beginning. And it continues to unfold. The birth of the universe is the first chapter in a story that spans billions of years. It is the foundation of everything that will follow in this series. From the first stars to the fate of the cosmos, this journey begins here, in the moment when time itself was born. Part 2. The first stars and galaxies. After the birth of the universe, there was a long silence. A silence without sound, without light, without form. The universe had expanded and cooled, but it was still dark. This period is known as the cosmic dark ages. For millions of years, nothing existed except vast clouds of hydrogen and helium drifting through an ever-growing space. Gravity was the only force shaping this darkness. It pulled matter together slowly, patiently, gathering tiny clumps into larger ones. These clumps would become the first structures in the universe. In this darkness, small differences in density began to grow. Some regions had slightly more matter than others. Gravity strengthened these regions, pulling in more gas, making them denser and heavier. Over millions of years, these clouds collapsed under their own weight. As they collapsed, they heated up. Deep inside these clouds, pressure increased. temperatures rose. The universe was preparing for its first light. Then, after hundreds of millions of years, the first stars ignited. They were unlike the stars we see today. They were enormous, hundreds of times more massive than our sun. They burned fiercely, shining with a brightness that pierced the darkness of the early cosmos. These first stars are called population E stars. They were made almost entirely of hydrogen and helium. They had no heavier elements. They were pure, ancient, and powerful. When these giants lit up, the cosmic dark ages ended. The universe was no longer silent. Light spread across space for the first time. Ultraviolet radiation from these stars began to change the surrounding gas. It ionized hydrogen, stripping electrons from atoms, creating bubbles of hot glowing plasma. This process is known as reionization. It transformed the universe from a cold, neutral fog into a transparent, illuminated cosmos. The first stars lived fast and died young. Because they were so massive, they burned through their fuel quickly. Many of them ended their lives in titanic explosions called supernovae. These explosions were powerful enough to forge heavier elements: carbon, oxygen, nitrogen, iron. Elements that would one day form planets, oceans, and living beings. When these stars exploded, they scattered these elements into space. The universe was no longer made of only hydrogen and helium. It now had the ingredients for complexity. As the first stars formed and died, gravity continued its work on a larger scale. Stars began to gather into groups. These groups grew into clusters. Clusters merged into even larger structures. Over hundreds of millions of years, the first galaxies were born. They were small, irregular, and chaotic compared to the galaxies we see today. But they were the first islands of light in a vast cosmic ocean. Inside these early galaxies, new generations of stars formed. These stars were smaller and lived longer than the first giants. They contained heavier elements created by earlier supernovae. This allowed them to form planets, moons, and more complex structures. The universe was becoming richer, more diverse, more dynamic. As galaxies grew, they began to interact. Some collided, some merged, some tore material from each other through tidal forces. These interactions shaped the structure of the universe. Over billions of years, galaxies formed into clusters and superclusters. They arranged themselves along vast cosmic filaments, leaving enormous empty regions called voids. This pattern is known as the cosmic web. It is the large-scale architecture of the universe. The first stars and galaxies were the architects of everything that followed. They ended the cosmic dark ages. They created the first heavy elements. They shaped the structure of space. They set the stage for the formation of solar systems, planets, and eventually life. Without these early giants, the universe would still be a cold, dark sea of hydrogen and helium. Part 2 shows us that the universe is a story of transformation, from darkness to light, from simplicity to complexity, from scattered gas to organized structure. The first stars were the sparks that ignited this transformation. Their light still echoes across the cosmos. Their elements live inside every star, every planet, and every living being. The journey of the universe continues, shaped by the legacy of these ancient giants. Part 3. The life and death of stars. Stars are the engines of the universe. They are born, they live, and they die. And in their lives and deaths, they shape everything around them. Without stars, there would be no planets, no oceans, no mountains, and no life. Every atom in our bodies heavier than hydrogen was forged inside a star. To understand the universe, we must understand the story of stars. A star begins its life inside a cold cloud of gas and dust. These clouds drift through galaxies like silent, dark oceans. Gravity slowly pulls the gas together. As the cloud collapses, it forms a dense core. Pressure rises. Temperature climbs. Deep inside this core, atoms begin to collide with incredible force. When the temperature reaches about 10 million degrees, hydrogen atoms fuse into helium. This process releases energy. The core ignites. A star is born. Once a star ignites, it enters the longest and most stable phase of its life. This phase is called the main sequence. During this time, the star balances two powerful forces. Gravity pulls inward, trying to collapse the star. Nuclear fusion pushes outward, trying to expand it. The star remains stable because these forces are equal. Our sun is in this phase right now. It has been shining for more than 4 billion years. The size of a star determines its fate. Small stars burn slowly. They can live for trillions of years. Medium stars, like our sun, live for billions of years. Massive stars burn quickly. They shine brighter, hotter, and die much sooner. but their deaths are far more dramatic. As a star ages, it runs out of hydrogen in its core. Fusion slows down, gravity begins to win. The core contracts and heats up again. This new heat ignites helium fusion. The outer layers expand. The star becomes a red giant. Our sun will one day reach this stage. It will grow so large that it will swallow Mercury and Venus. Earth may survive, but it will be scorched and lifeless. For small and medium stars, the red giant phase is the final act. After burning the last of their fuel, they shed their outer layers into space. These layers form beautiful clouds of gas called planetary nebulae. At the center, the core remains as a white dwarf, a small, dense, glowing ember. Over billions of years, it cools and fades into darkness. Massive stars follow a different path. When they run out of fuel, their cores collapse violently. The collapse triggers a supernova, one of the most powerful explosions in the universe. For a brief moment, a single star can outshine an entire galaxy. Supernovae create heavy elements like gold, uranium, and lead. They scatter these elements across space. These elements become part of new stars, new planets, and eventually new forms of life. After a supernova, the core of the star becomes either a neutron star or a black hole. Neutron stars are incredibly dense. A teaspoon of neutron star material would weigh billions of tons. Black holes are even more extreme. Their gravity is so strong that nothing, not even light, can escape. They warp space and time around them. They are the most mysterious objects in the universe. The life and death of stars is a cycle. Stars are born from clouds of gas. They shine for millions or billions of years. They die and return their material to space. This material forms new stars, new planets, and new possibilities. Every generation of stars enriches the universe with heavier elements. With each cycle, the universe becomes more complex. Part 3 shows us that stars are not just points of light in the night sky. They are creators. They are destroyers. They are the architects of matter. The iron in our blood, the calcium in our bones, the oxygen we breathe, all of it was forged in the heart of a star. When we look at the night sky, we are looking at our own origins. The story of stars is the story of us. Part 4. The architecture of the cosmos. The universe is vast, but it is not random. It has structure. It has form. It has an underlying design shaped by gravity, time, and the slow evolution of matter. When we look at the night sky, we see stars scattered across darkness. But on the largest scales, the universe is organized into patterns far more complex and beautiful than anything we see from Earth. This is the architecture of the cosmos. After the first stars and galaxies formed, gravity began to shape the universe on a grand scale. Galaxies did not form in isolation. They gathered into groups, clusters, and superclusters. These structures stretched across millions of light years. They were connected by long, thin threads of dark matter and gas. These threads formed a vast network known as the cosmic web. It is the largest structure in the universe. It is the skeleton of the cosmos. The cosmic web is made of three main components. First, there are filaments, long, narrow bridges of galaxies and dark matter. Second, there are clusters, dense regions where thousands of galaxies gather. Third, there are voids, enormous empty spaces with almost no galaxies at all. These voids can span hundreds of millions of light years. They are the silent chambers of the universe. Dark matter plays a crucial role in this architecture. Although it cannot be seen, it makes up most of the universe's mass. It creates gravitational wells that pull normal matter toward them. Galaxies form inside these wells. Without dark matter, the universe would not have enough gravity to form the structures we see today. Stars, planets, and life would not exist. Dark matter is the invisible framework that holds the cosmos together. As galaxies formed along the filaments of the cosmic web, they began to evolve. Some galaxies grew large and spiral-shaped, like our Milky Way. Others became elliptical, smooth, and featureless. Some remained small and irregular. The shape of a galaxy depends on its history, how it formed, how it interacted with its neighbors, and how much gas it had available for star formation. Galaxies are not static. They move through space. They collide. They merge. When two galaxies collide, their stars rarely hit each other directly because the distances between stars are enormous, but their gas clouds interact. They compress. They trigger bursts of star formation. Collisions reshape galaxies, turning spirals into ellipticals or creating new structures like tidal tails and star-forming rings. The universe is constantly sculpting itself. At the center of most large galaxies lies a supermassive black hole. These black holes can be millions or even billions of times more massive than the Sun. They influence the motion of stars around them. When gas falls into these black holes, it heats up and emits powerful radiation. Some galaxies become active, shining brightly from their centers. These active galaxies can shape their surroundings, pushing gas outward and affecting star formation. The architecture of the cosmos is not fixed. It evolves over billions of years. Galaxies drift along the filaments of the cosmic web. Clusters grow larger as they pull in more galaxies. Voids expand as matter flows away from them. The universe is dynamic, always changing, always moving. Even now, the Milky Way is on a collision course with the Andromeda Galaxy. In about 4 billion years, the two galaxies will merge into a single, larger galaxy. This is part of the natural evolution of cosmic structure. The large-scale structure of the universe reveals something profound. Despite its vastness, the cosmos is connected. Every galaxy, every star, every planet is part of a larger pattern. The cosmic web stretches across the universe like a vast network of roads and bridges. It shows us that the universe is not chaos. It is order. It is structure. It is design shaped by the laws of physics. Part 4 reminds us that the universe is not just a collection of isolated objects. It is a single, interconnected system. Galaxies form, move, and evolve within this system. Stars are born and die within galaxies. Planets form around stars. Life emerges on planets. Everything is part of the same cosmic architecture. The story of the universe is the story of structure rising from simplicity, order emerging from chaos, and complexity growing across billions of years. Part 5: The Formation of Solar Systems. As galaxies matured and filled with new generations of stars, the universe entered a period of increasing complexity. Stars were no longer forming alone. They were forming with companions, disks of gas and dust swirling around them. These disks were the birthplaces of solar systems. They were chaotic, violent, and full of potential. From these swirling clouds, planets, moons, asteroids, and comets would one day emerge. A solar system begins with a molecular cloud collapsing under its own gravity. As the cloud contracts, it spins faster, forming a flattened disk around a growing central star. This disk is called a protoplanetary disk. It contains hydrogen, helium, dust grains, ice particles, and the heavier elements created by earlier generations of stars. These elements are essential. Without them, planets like Earth could not exist. Inside the disk, dust grains collide and stick together. At first, these grains are tiny, smaller than grains of sand, but over time they grow into pebbles, then rocks, then boulders. Collisions continue. Some fragments shatter, others merge. Slowly, larger bodies form. These bodies are called planetesimals. They are the seeds of planets. As planetesimals grow, their gravity strengthens. They begin to pull in more material. Some become protoplanets, early versions of planets. The disk becomes a battlefield of collisions, mergers, and near misses. Some protoplanets grow large enough to clear their orbits of debris. These become full-fledged planets. Others are destroyed or absorbed by larger neighbors. The early solar system is a place of constant change. The location within the disk determines what kind of planet can form. Close to the star, temperatures are high. Only rock and metal can survive. This is where terrestrial planets form. Small, dense worlds like Mercury, Venus, Earth, and Mars. Farther from the star, temperatures drop. Ice can survive. Here, giant planets form. They begin as rocky or icy cores, then pull in massive amounts of gas. This is how Jupiter and Saturn formed. Even farther out, icy giants like Uranus and Neptune take shape. While planets form, the young star at the center continues to grow. It pulls in material from the disk. It heats up. Eventually, nuclear fusion ignites in its core. The star begins to shine. Its radiation and stellar winds blow away the remaining gas in the disk. This marks the end of planet formation. What remains is a new solar system, a collection of planets, moons, asteroids, and comets orbiting a stable star. Moons form in several ways. Some form from the same disk as their planets. Others form from giant impacts. Earth's moon likely formed when a Mars-sized body collided with the early Earth. The debris from this impact gathered into a disk and eventually formed the moon. Other moons are captured objects. Asteroids or dwarf planets pulled in by a planet's gravity. Each moon carries a unique history. Asteroids and comets are the leftover building blocks of the solar system. They are ancient, unchanged for billions of years. Asteroids are rocky. Comets are icy. They orbit the star in vast belts and clouds. Sometimes they collide with planets, delivering water, organic molecules, and other essential ingredients for life. These impacts may have played a crucial role in shaping young worlds. The formation of a solar system is not a quiet process. It is violent, chaotic, and full of destruction. But from this chaos emerges order. Planets settle into stable orbits. Moons circle their hosts. Debris clears. The system becomes calm. Over billions of years, conditions stabilize enough for life to appear. At least on some worlds. Part 5 shows us that solar systems are not accidents. They are natural outcomes of the universe's evolution. They form from the same processes that shape stars and galaxies. They are built from the ashes of earlier generations of stars. Every planet, every moon, every grain of sand is part of a cosmic cycle billions of years old. Our own solar system is just one example of this universal pattern. And somewhere in the vastness of space, countless other systems are forming right now, each with its own story, its own worlds, and its own possibilities. Part 6. The emergence of life. Life is one of the rarest and most remarkable phenomena in the universe. It requires the right conditions, the right chemistry, and the right environment. But before life can begin, a planet must first become a home. This journey starts long before the first cell appears. It begins with the formation of a stable star, a solid planet, and the delicate balance of temperature, water, and atmosphere. On young planets, the surface is often hostile. Volcanoes erupt, meteorites fall, oceans boil and cool, the atmosphere shifts between chaos and calm. But within this turbulence lies opportunity. The early Earth was such a world. It formed from dust and rock left over from the birth of the sun. Collisions heated its surface. Radioactive elements warmed its interior. Over time, the planet cooled enough for oceans to form. Water became the stage on which life would begin. Life requires complex molecules. These molecules form from simple ingredients: hydrogen, carbon, oxygen, nitrogen. These elements were created in ancient stars and delivered to young planets by comets, asteroids, and interstellar dust. In the early oceans, these elements combined into organic molecules. Amino acids, lipids, and simple sugars formed naturally under the right conditions. Lightning, ultraviolet radiation, and volcanic heat provided the energy needed for chemical reactions. Over millions of years, these molecules assembled into more complex structures. Some formed membranes, others formed chains capable of storing information. Eventually, a molecule emerged that could copy itself. This was the beginning of biological evolution. Once replication began, natural selection took over. Molecules that copied themselves more efficiently became more common, complexity increased. Chemistry became biology. The first true life forms were simple. They were single-celled organisms floating in the oceans. They had no eyes, no limbs, no nervous systems, but they could grow, reproduce, and adapt. They were the ancestors of every living thing on Earth. These early organisms transformed the planet. Some learned to use sunlight for energy. They released oxygen as a byproduct. Over hundreds of millions of years, oxygen accumulated in the atmosphere. This allowed more complex life to evolve. Life is resilient. It adapts to extreme environments. It thrives in boiling vents at the bottom of the ocean. It survives in frozen deserts. It endures in acidic lakes and deep underground. This resilience suggests that life could exist elsewhere in the universe. If life emerged on Earth from simple ingredients and natural processes, it may have emerged on other worlds as well. Planets orbiting stable stars may have oceans, atmospheres, and the right temperatures for life. Some moons in our own solar system, Europa, Enceladus, Titan, may have subsurface oceans warmed by tidal forces. These environments could support microbial life. The universe is vast, with billions of galaxies, each containing billions of stars. The number of potentially habitable worlds is enormous. The emergence of life is not just a scientific event. It is a turning point in the story of the universe. For billions of years, the cosmos was filled with stars, gas, and dust. But with life, the universe gained something new: the ability to observe itself. Living beings can sense, think, and reflect. They can ask questions about their origins. They can explore the cosmos that created them. Part 6 shows us that life is both fragile and powerful. It arises from simple chemistry, yet it transforms entire planets. It begins in darkness, yet it reaches for the light. The story of life is the story of complexity emerging from simplicity, of order rising from chaos. And in this story, we are participants. We are the descendants of ancient molecules that learned to replicate, adapt, and evolve. The universe gave rise to life, and life in turn gives meaning to the universe. Part 7. The future of the universe. The universe has a past, a present, and a future. Its story did not end with the formation of stars, galaxies, or life. It continues to unfold across billions of years. To understand where the universe is going, we must understand the forces that shape it: gravity, dark matter, dark energy, and the slow aging of stars. The future of the cosmos is written in these forces today. The universe is expanding. Galaxies are moving away from each other. Distant galaxies recede faster than nearby ones. This expansion is driven by something mysterious called dark energy. Dark energy makes up most of the universe. It pushes space apart, it accelerates the expansion, and it will determine the ultimate fate of everything that exists. In the near future, on cosmic timescales, stars will continue to form. Galaxies will continue to evolve. Collisions between galaxies will reshape their structures. Our own Milky Way is on a path toward the Andromeda Galaxy. In about 4 billion years, the two galaxies will merge. Their stars will swirl together, forming a new, larger galaxy. The Sun will still exist at that time, but Earth will no longer be habitable. Long before the merger, the Sun will expand into a red giant, transforming the inner solar system. As time passes, star formation will slow. Galaxies will use up their gas. Fewer new stars will be born. The universe will grow older and dimmer. The bright, active era of star formation will fade. Eventually, only long-lived red dwarf stars will remain. These stars burn slowly and can shine for trillions of years. They will be the last lights in a darkening universe. Far into the future, even these stars will exhaust their fuel. They will fade into white dwarfs, then into cold, dark remnants. Black holes will dominate the cosmos. They will consume nearby matter. They will merge with each other. Over unimaginable timescales, even black holes will slowly evaporate through a process called Hawking radiation. The universe will become a place of faint particles, thin radiation, and expanding emptiness. This distant era is known as the heat death of the universe. It is not an explosion or a collapse. It is a slow fading, a gradual decline into darkness. Energy becomes evenly spread. No new structures can form. No new stars can ignite. The universe becomes quiet, cold, still. But this is only one possible future. Some theories suggest that dark energy could change over time if it grows stronger. The expansion of the universe could accelerate so rapidly that galaxies, stars, planets, and even atoms would be torn apart. This scenario is called the Big Rip. It is dramatic, but uncertain. We do not yet know whether dark energy is constant or evolving. Another possibility is the Big Crunch, a future in which the expansion slows, stops, and reverses. The universe would collapse back into a dense state, ending as it began. But current observations suggest that expansion is accelerating, not slowing. The Big Crunch seems unlikely, but the universe has surprised us before. The future of the universe is shaped by forces we are only beginning to understand. Dark matter holds galaxies together. Dark energy pushes them apart. Gravity shapes stars and planets. Time transforms everything. The cosmos is a balance of creation and decay, of light and darkness, of beginnings and endings. Part 7 reminds us that the universe is not eternal in its current form. It evolves, it changes, it ages. But even in its distant future, the universe carries the legacy of everything that came before. The first stars, the first galaxies, the first living beings, all of them are part of a story that spans billions of years. A story that continues to unfold. And in this vast cosmic timeline, our moment is brief, but it is meaningful. We are the universe becoming aware of itself. We are the observers of its past, the witnesses of its present, and the thinkers who imagine its future. The story of the universe does not end with darkness. It continues in every question we ask, every discovery we make, and every moment we spend looking up at the night sky. Thank you for listening this story and spending your time exploring the universe together with me. If this journey was meaningful to you, feel free to press like, share it with someone who might enjoy it, and subscribe to the channel for future documentaries. And if you have ideas, questions, or topics you would like to see explored next, write them in the comments. Your thoughts help shape what comes after.